You've probably seen pictures of a nuclear reactor, right? And if you have, you've definitely seen that incredible, almost alien-looking blue glow. It's one of the most iconic images in all of science. But what's actually causing it? Well, let's dive in and figure out what's behind this spectacular phenomenon.
And there it is, this absolutely mesmerizing blue light coming from the core of a research reactor, which is submerged in this big pool of water. It's beautiful, yeah, but also kind of eerie, and it is definitely not just for show. This glow is a real physical phenomenon, a signature of just immense energy at work.
So, what is the deal with this strange blue light? The answer is just fascinating, and it's going to take us on a journey from a surprising discovery back in the 1930s all the way to the very edge of astrophysics today.
Okay, so let's start at the beginning. We need to wind the clock back a bit to the person who first scientifically documented this whole thing.
So picture this, it's 1934, and a Russian physicist named Pavel Cherenkov is the first to really observe and study this radiation. But, just seeing it wasn't enough. It actually took the brilliant theoretical work of his colleagues Ilya Frank and Igor Tamm to fully explain what on earth he was looking at. And their combined effort, so fundamental, so groundbreaking, that all three of them shared the Nobel Prize in Physics for it in 1958. All right, now for the really cool part, the explanation. Honestly, the best way to wrap your head around this glow is to imagine a sonic boom, but for light.
This right here is what we call Cherenkov radiation. It happens when a charged particle, say an electron shooting out from a nuclear reaction, zips through a medium, like water, faster than the speed of light in that medium. Now that last part, in that medium, is absolutely crucial.
And I know what you're thinking. Wait a minute, hold on. I thought nothing could travel faster than the speed of light. And you're not wrong, but there is a very, very important catch.
See that universal speed limit, the one from Einstein? That applies to the speed of light in a total vacuum. But when light passes through a transparent material, like the water in that reactor, or even glass, it actually slows down.
And how much does it slow down? Well, in water, light travels at only about 75% of its absolute top speed. That slowdown creates this tiny window of opportunity, a loophole, for a super fast particle, like an electron from the reactor core, to literally overtake the light.
And this is where that analogy just clicks into place. You know how a jet creates a sonic boom when it breaks the sound barrier in air? It's creating a shock wave of compressed sound waves. Well, it's the exact same idea here. When that electron breaks the light barrier in water, it creates an electromagnetic shock wave. And instead of sound, this shock wave is made of light particles, photons. It is, quite literally, a sonic boom of light.
Okay, so we've got a shock wave of light. I'm with you. But why is it always that very specific, characteristic blue color?
The answer to that really comes down to the energy of this shockwave. This isn't some gentle ripple in a pond. It is a high-energy event. The photons of light it kicks out are packed with a ton of energy, which means they have a very short wavelength. They're also emitted in this really distinctive cone shape, which is a key signature scientists actually look for.
So if you think about the visible light spectrum, a rainbow, the colors with the highest energy and the shortest wavelengths are way over on one side, blue and violet. So when this high-energy shock wave of light hits our eyes, what we see is that brilliant blue. The Cherenkov effect is just naturally tuned to the blue end of the spectrum.
Now, this glow isn't just a pretty side effect of physics. Oh no. It is an incredibly useful tool for both science and for safety. So let's take a look at how it's actually put to work.
I mean, this quote from the International Atomic Energy Agency really says it all. The intensity of that Cherenkov glow is directly tied to the power of the reactor. This means inspectors and operators can safely monitor nuclear fuel just by, looking at the light it produces. It's a hands-off, safe, and totally transparent way to keep tabs on nuclear materials.
And here's the proof in the pudding. On the left, that's the signal from a power meter that just measures the brightness of the Cherenkov light. On the right, that's a signal from a traditional neutron detector. I mean, look at them. They're practically identical. This just goes to show that measuring this glow is a super reliable and independent way to monitor a reactor's power in real time.
But the applications go way beyond reactors. We're talking cosmic scales here. When super high-energy gamma rays from, say, an exploding star slam into our atmosphere, they create this whole cascade of particles that travel faster than light in air. Now, we can't see the gamma rays themselves,
but we can see the quick blue flash of Cherenkov light they create. And these giant telescope arrays, with awesome names like Magic, Hess, and Veritas, they're built specifically to catch these faint, super-fast flashes, letting us study the most violent events in the entire universe.
And the list of uses is just incredibly diverse. Particle physicists use the precise angle of that light cone to identify different particles. In medicine, it's being used to check the exact dose of radiation delivered during cancer therapy. And, like we've seen, it's absolutely vital for nuclear safeguards, making sure these materials are being used peacefully.
So, what started out as just this weird, curious blue glow in a lab is now this fundamental tool for humanity. It helps us keep nuclear energy safe, it lets us peer into the hearts of distant galaxies, and it can even improve medical treatments. It really makes you wonder, what other secrets is this beautiful shockwave of light just waiting to reveal to us next?